are going to discuss on ductile iron. So, in the last two lectures I have discussed about the iron graphite phase diagram as well as iron carbide phase diagram to tell you the difference between the eutectic reactions when silicon is present in the system. Then finally, we also discussed about the gray iron. As you have seen in the last part of my last lecture, I told you that the flux in the gray iron create problems when the stress concentration is an issue in the material. That is mean that if I consider this flux in the graphite, let me go back a little bit and tell you, if you consider the flux in the graphite, suppose these are the flux in a gray iron matrix. As you see here, every flux has an end, and end is very fine, it is very thin, of the order of few tens of nanometers. So, because of this small diameter of the ends of the flux, once a load is applied to the material, it can lead to huge stress concentration at the tip, and the stress concentration can be very severe, in the sense that this can lead to crack generation at the tip and material can fail. And these other things have been observed on the, well, this is the main problem of gray cast iron, although it has many disadvantages, like it can have good ductility, good lubrication ability, also good thermal conductivity, which is required, and good castability obviously, which are required for the cylinder block of the engine in the automobile components. Therefore, this particular problem of stress concentration, which just now I discussed, requires a solution, and the solution, by the way, is very simple, very simple theoretically obviously. What is it? If I make this flux from flake to let us say spheroidal, that is what I showed you at the beginning of this lecture, last lecture. Yes, instead of this flux here, you see, if I make them circular or round, then there will be no issue of stress concentration, because it is a circular particle. So, therefore, surface area is known and it is uniform. So, amount of load you apply, you know the stress generated, and this is the reason, another reason why spheroidal graphite iron or nodular iron or ductile iron has been prepared. And so, in today's lecture we are going to discuss in detail how that thing happened. So, pioneer in the field of ductile iron is George and Fisher, two scientists from UK, who actually developed a George Fisher converter, in which a gray iron can be converted to spheroidal graphite iron. So, let us first discuss. So, I give you an idea that the problem in the gray iron led to the discovery of ductile iron. Now, you know, in ductile iron all the graphite spheres are actually spherical, and if you look at carefully, these spheres are basically surrounded by a very ductile matrix called ferrite. Well, if you go away from these spheres, you have a pearlite, only around it there is a ferrite. We will discuss why it is so. This is called bull's eye structure. This whole thing is called bull's eye. If you see a bull's eye, if you see any bull's eye, you will see this kind of things. Well, the matrix can be fully ferritic also, like this one at the bottom. This is a completely ferritic matrix. This is paralytic matrix. So, now the question is that how this long flux in gray iron is converted into round graphite affairs. This is mostly done by addition of few elements in the melt. The first one is magnesium or cerium or mixed metal. Mixed metal is MiSCH is is a mixture of rare earths, cerium and many other rare earths, dysprosium, so many rare earth metals are there, it is a mixed metal. So, earlier days magnesium used to be the main material in which this conversion from flaky graphite to circular graphite used to happen. But you know magnesium, and this was done in a George Fisher converter. Magnesium is basically has a low vaporization temperature, it is about 1160, and the cast iron melting temperature is also similar to that, about 1200 degree. So, therefore, magnesium is basically used to get evaporated, and that is the reason why cerium and mixed metal also came into picture. So, that is the second characteristics. This cerium, magnesium or mixed metal is to be added to make this conversion from the flaky graphite to a circular graphite. Matrix can be ferritic or perlitic. Usually perlitic matrix is better because this is hard, and many cases the matrix can be hardened also and made martensites possible. Well, you know cast irons with tensile ductility can be formed by adding this magnesium, cerium, lithium or sodium. Sodium is not rarely used, magnesium, cerium, calcium just before casting. This additive cause the graphite to form as a teeny tiny balls or spherulites rather than flakes during the eutectic solidification of grey iron. Since magnesium is above its boiling temperature, the casting temperature, magnesium is basically boils at about 1160 degrees Celsius temperature, but casting temperature can be as high as 1300 1400 degrees Celsius temperature. So, it is necessary to add magnesium in alloy form. Normally magnesium nickel alloys are added, or otherwise you can do a George Fisher converter in which magnesium is kept at the bottom of a huge liquid of grey iron and evaporation can be stopped. So, basically the concept which you are getting is that this magnesium, cerium, calcium, they basically do something so that the shape of the graphite changes from flakes to spherical. Now, if you are a little bit intelligent and clever, it is very easy to understand or very easy to think about it, but that is not the way. The difference between a flake and a sphere is that the surface area of a sphere is much lower per unit volume than a flake. So, is it because of the surface area reduction? Answer is no. Answer is that magnesium actually removes the sulfur from the melt, and the sulfur actually poisons the graphite growth morphology. In a few lectures ahead it will be clear to you much more. So, now if you see here, this is what I am showing you. Let me just show you first microstructure, then discuss. You can have a spherical graphite nodules in a ferritic matrix or a graphite nodules in a perlitic matrix, but in this case also graphite nodules are surrounded by ferrite, then the perlite comes. Well, let us first discuss about, we will come back to these issues. So, let us first discuss about the shapes of these nodules. Although I am telling you these nodules are actually of spheres, but they are not spheres. They are actually, they have a shape of a thatched roof, as you see here. This is the peak of the roof, and these are the graphite things joined like this. Join like this. I mean, it is much clear here in this picture. You see, these are the graphite. Okay, there are blobs. There are actually 1, 2, 3, 4 compartments, and this is one is this. So, it is very clear this is not a sphere. On the other hand, the structure is like this. This is what it is, or it is better I can draw it like this. This is like a thatched roof you see in phantom movies, and in fact the matrix here is perlitic, as you see here, and much more clear picture will come to here. This is ACM picture of one such nodule. You see here the different contrast, black and grey contrast. So, that means there are different crystals, and one can actually use EBSD, electron back scatter diffraction. Then you can map the crystallographic orientation of these, and if you see clearly there are different orientation. There is a magenta color, there is a blue color, there is a some other color. So, there are 3-4 different orientation within the graphite nodule. So, what actually happens is that flakes of the graphites are like this, they are like fibers. Now, let me see whether I have such things. No. So, these flakes actually then form, they rotate and form a structure like this, So, that is what actually happens and form. Therefore, the structurally the gray iron, the graphite flakes in gray iron is similar good morphology wise and the SG iron, although this sentence is not fully correct, but I am making it because what we are changing is only the way the graphite flakes or graphite fibers is basically arranging, that is what we are changing in spherical graphite iron, and this mainly happens because of the removal of sulfur. So, magnesium removes the sulfur, magnesium from magnesium sulfide, the sulfur goes removed, and sulfur amount when it is become very low, it is about 0.01 percentage. Normally, it is actually theoretically speaking, it should be less than about 0.054 percentage weight percent of sulfur remain in the melt, so that sulfur cannot poison. Basically, sulfur actually poison the growth of this graphite, and that is how the flakes forms. So, if we remove the sulfur, it cannot poison, then these low energy configurations of graphite can come into picture, and that is exactly what happens. Now, all the sulfide forming elements cannot be added because they can react, like you can add cadmium form very easily sulfide, but cadmium reacts with the melt, and not only that it can oxidize very fast. So, that is why magnesium or calcium or cerium is better off. Calcium forms sulfide very easily. Those of you know a little bit of steel making, they know that calcium carbide, calcium slag is used to remove the sulfur, or desulfurization of the steel is basically done by adding sulfur. So, that means basically these elements remove the sulfur from the melt and make the melt cleaner, so that graphite can take its low energy configuration, and the low energy configuration is this nodule. So, I hope this is very clear to you that graphite is not a sphere, it is basically a nodule with different orientations, and which is shown in this picture much nicely. So, this has a tremendous effect on the mechanical properties. First and foremost thing is that stress concentration is removed, as is the case for gray iron. So, that part is gone. Stress is uniformly distributed across this interface of the nodule. So, that is why these spherical graphite iron or nodular iron is widely used in the load bearing applications, where the toughness requirement is high, like housings. In all these automobile, the housing, rear axle housing, front axle housing, gearbox housing, they are made up of these spherical graphite irons, because they can absorb lot of impact energies. When a car moves on a bumpy road, the huge impact happens, and this impact can break away these housings. So, that is why these housings are made up of this casting. Another picture of this graphite, you can see here is the SEM picture, which is a heavily etched sample, and these are the different things. This is just like a cabbage again, the one I have shown you for the gray iron, but it is a nodule. So, this part of the thing has been etched out, correct. Now, to give you an idea comparative things, there are different matrices, as I said to you. You have ferritic matrix, perlitic matrix, and these are the different steel compositions. If you look at the ductility, you could see here ferritic matrix has a 20% ductile than things, and then the perlite. This is the case for malleable iron. Malleable iron we will discuss later. Malleable iron is basically very ductile, but if you say nodular, you can actually achieve about 12% ductility, which is practically good, and perlite also it's about 5% ductility. Strength wise you gain, you do not lose much, it is a 158 MGPa, sorry, this is modulus. Strength wise you gain lot, 448 or 655 you can see, as compared to on the malleable iron. Malleable iron we will discuss, and then we can come back to this table again. So, basically we just get a good combination of strength and ductility by making the spherical graphite iron. Okay, so that is the part of the what's called, that is the part of the spherical graphite iron, but I think I just wanted to tell you one more thing before we wind of this lecture. So, as you have seen, in case of gray iron, the graphites can have different the flex size wise, shape wise. Basically, you have rosettes, you have short fibers, long ones, oriented, or you can have random. But those that means you have many ways of arranging the graphite of the getting the different graphite flex. You do not have that. You have very less limitations on this. Okay, yeah. That another important thing I forgot to tell. You have very less limitation on these. Obviously, you have only spherical ones particular shape. So you do not have much control on the mechanical variation of mechanical properties. Well, now the question I need to answer is that why does this bullseye form? Okay, so normally once this graphite nucleate in the liquid, because graphite will nucleate at high temperature, graphite is a high melting temperature. So for the growth of the graphite, it requires a lot of carbon. So what happens? It takes away the nearby carbon, it absorbs all the nearby carbon because it needs to grow and become bigger. So nearby thing will be very lean in carbon. That is why the nearby region becomes ferritic, because it is again same thing. The things forming transformation is again liquid transforming to gamma plus graphite. So if the graphite nodules forms and you have a gamma matrix, this is gamma, and what will happen? It takes away all the carbon from the nearby gamma, it takes away all the carbon. So because it takes away all the carbon from the nearby gamma, the nearby region will be depleted of carbon. So these gamma then will convert to alpha at low temperature, but on the other hand far away regions will transform to pearlites, because the carbon content will remain quite high there, and that is the reason it is bullseye form normally, but there are other takes on that. Now question is that if I keep the sample at high temperature for a long time, these graphite nodules will keep on growing, and as they keep on growing, what will happen? They will take all the carbon from the matrix or from the regions nearby. If they take away the carbons, that region, the gamma iron will be depleted of carbon, whole gamma iron sample depleted of carbon, and once it become depleted of carbon, it will take away all the carbon from these regions and this matrix will become ferritic. That is the way you can create both the paralytic and ferritic matrix. So therefore I told you that these are the basic features of the nodular iron. Now in the next lecture I am going to discuss about malleable iron, which is also an important material used in the space industry, and I will tell you how things are done and what is the theory behind it.